Would you believe me if I told you that the water that comes into your home is cleaned by bacteria? Many drinking and wastewater treatment plants around the world use a process called biological nutrient removal, which means that their treatment systems are designed to encourage the growth of bacteria responsible for removing harmful nutrients in water. In fact, conventional wastewater treatment systems heavily rely on the use of microorganisms to make our water safer. This does sound a little odd because one would think, wouldn't we want our water to be free of bacteria and any harmful microbes? So the question becomes, how do we involve these species in our water treatment processes and actually benefit from the role they play in water treatment? My name is Fatima, and I am a PhD student in environmental engineering, currently studying the role of microorganisms in cleaning wastewater. In this video, I will aim to tackle this very interesting question while taking you on a tour of a municipal wastewater treatment plant. When I first started my research, I actually had no clue of the huge role that tiny microbes play in cleaning our water. Upon spending some time learning about this topic, I became amazed at how much potential and influence these microscopic life forms have on influencing the state of what is arguably the most essential resource on Earth. I also became more aware of all the intricacies and essential steps involved in preserving the safety of this vital resource. I hope this video allows you to relate to my amazement at all the important details that make up the wastewater treatment methodology. So, without further ado, let's get into what makes up conventional wastewater treatment systems, like the one you would find treating your own home's wastewater. Our tour is located at a wastewater treatment plant designed to treat water coming from homes and buildings within a small city in southern Ontario, Canada. Wastewater is cleaned so that it is safe to return back into environmental waters, such as nearby rivers and ponds. We start off at this spiral structure, which is rotating in the midst of this pool of dirty water. This dark-colored volume of water is wastewater, also referred to as sewage. The spiral structure acts as a barrier that prevents larger debris such as jewelry, papers, and food scraps from continuing forward in the water treatment plant, and this debris or garbage is disposed of in municipal waste landfills. This is a form of screening to make sure that the wastewater is ready to enter the rest of the treatment system and that larger waste will not impact the quality of water treatment or the plant's treatment technology negatively. A step with a fairly similar purpose is employed next. The water from the previous screening pools flows to this area here, where the next step is grit removal. Any large debris, such as sand or large particles left over, settle down at the bottom of this pool. The settled grit is also sent to landfills for waste disposal. Using both the screening and grit removal steps ensures that the water is free of larger particles. As you can see, there is a small pipe continuously adding a brownish yellow colored liquid chemical into the grit removal pool. This chemical is called ferric chloride, and it helps smaller solid particles aggregate together so that they can settle at the bottom of the pool faster, and so that it is less likely that many small solid particles will be left in the wastewater pool. It is also very common for plants to use aluminum chloride instead of ferric chloride to perform this step, which is called coagulation. Now that most of the solid materials are removed, the water is ready to be treated to remove much smaller harmful particles. The next stop on our tour is the primary settling tank. Here we see a vast array of primary settling tanks running parallel to one another. Denser materials that are left in the wastewater settle at the bottom of these tanks, similar to what we observed in the grit removal pools. In these tanks, however, the materials that settle downward are a combination of microorganisms, organic nutrients for these microorganisms, and inorganic substances, a mixture that is called scum, or primary sludge. This material is collected on the base of the tanks and manually scraped off regularly. While the scum is removed from wastewater, it is actually very special and very useful for wastewater research and even in the treatment of wastewater, as it is often recycled within the system, and the microorganisms from the sludge can at times be useful for the next step, which is called aerobic treatment. Here we see the aerobic treatment tanks. It may look like this water is very dirty, since its color is brown. However, we want our water to look exactly like this at this stage of treatment. The brownish color here is coming from microorganisms that are involved in removing nitrogen from the wastewater. Nitrogen, such as in the form of ammonia, has the potential to be extremely harmful and toxic in water. If wastewater that is returned to the environment is high in nitrogen, it will result in the rapid depletion of oxygen in these environmental waters through a process called eutrophication. When there is lots of nitrogen available for aquatic plants to consume as a nutrient source, they begin to grow uncontrollably. When these plants die and begin to decay, the process of their decomposition by aquatic microorganisms is heavily oxygen reliant, which quickly diminishes the oxygen supply available for other aquatic life. Nitrogen concentrated water is also very dangerous for human consumption. If we go back to our question, how do we involve these microbial species in our water treatment processes and benefit from the role they play in water treatment? We can see now that microorganisms play an extremely important role in water treatment. In fact, not only is this process, which is called biological nitrogen removal, highly effective in removing nitrogen from water, but it is also very energy efficient, cost effective, and employed as an essential part in all conventional wastewater treatment systems around the world. Not only are these biotanks being used for nitrogen removal, but we are exploring how we can develop our biotanks to promote microorganisms to remove other kinds of harmful nutrients in wastewater, such as phosphorus, which also promotes eutrophication. The next to last treatment stage of the wastewater involves passing the treated water through a secondary form of treatment, which at this plant was a set of rotating biological contactors. The water flows into these cylindrical tanks where there are several rotating metal discs inside. Each metal disc also has microorganisms attached to it in a slimy covering called biofilm, and the biofilm also helps with nutrient removal. The treated water from here goes to a final settling tank called a clarifier before it goes to the last stage of treatment. In this building, the clean water is treated with sodium hypochlorite, a type of chlorine treatment for disinfection. While the microorganisms were very helpful to us in the process of water treatment, it is unfortunate that any of them that made it to this very last step will have to die to maintain adequate biological control of the treated water. The chlorine kills these microbes so that they cannot be harmful in environmental waters. Many facilities, including the one in this tour, are looking into completely relying on UV radiation as a means of disinfection, since disinfectant chemicals like chlorine can produce harmful byproducts. Finally, we get to see the product of all the hard work that goes into treating the wastewater end up in the local river. The water is now safe for aquatic life and for humans too, who will also likely come into contact with it. It's amazing how many steps and how much thought and design goes into a regular process such as water treatment, something that many people don't know much about. And each step of the process requires great understanding, purpose, skill, and planning. I feel like I could spend my whole life researching my PhD topic, which is on a single small aspect of the wastewater treatment system. Yet, I would still relate it to reading the first page of a book with 1,000 chapters. The continuous knowledge expansion in my field, even on minute details of water treatment, reminds me that there is always so much more to what may be seemingly simple. And no matter how much we learn about something, there will be always so much more to explore and to discover.